I said, huh? And I think that I suspect there are a couple of delicate points that haven't been completely checked, but I couldn't insist too much with the authors, and certainly. All right. So what did we want to do? We wanted to say something about the connection between the kinds of things we've been doing and zeta functions of algebraic variety. So I just remind you, I think we'll just do it abstractly now. Say if we have a variety V over F, so F is a number field. This variety V is supposed to be sort of nice, smooth, projective. Then we can define, and I may come back to this, I may not come back to it, depending upon the time. It's zeta function, which is a function of a complex variable S. And the formal theory says that this zeta function is a quotient of products of L functions, 1 up to twice d is the dimension of the variety, divided by similar things, and Li of SV is the kind of L function we considered before. So it's, if I ignore a finite number of primes, it's the product over P of 1 over 1 minus alpha 1 of P, norm of P to the S, 1 up to 1 minus alpha B sub I of P over norm of P to the S, where this is the ith Beatty number of the variety. So these are this kind of L function we considered before. And of course, what we said before is that the goal of one of the goals, primary goal, is to show that for any variety, this L of SV is equal to L of the L function associated to an automorphic form representation pi, where pi is an automorphic representation of GLB. So let's put here GLBI AF. So pi is an automorphic representation of that. It depends upon I. So for each I, we'd like to prove such a theorem for all varieties. Now, something that's trivially equivalent statement is to say that Li of S and V is equal to a product of the following form: L of S pi 1 I up to L of S pi sub mi I, where so pi, let's drop this. I mean, the I is implicit. Pi I is an automorphic representation of GL some Ni of Aj, and the summation, or Nj, and the summation of these numbers Nj is the total degree Bi. This statement, it would be just as good to prove this statement. It's trivially equivalent. Now, A sub F. Now, if functoriality is granted, then an equivalent statement would be there exist groups G1 up to Gm, representations R1 up to Rm of the L group, and automorphic representations pi 1 up to pi m. So let's say pi j. So representations Rj of GLJ, an automorphic, so this is the L group, so these are finite dimensional complex representations, automorphic representations of G, J of AF. So the Rj are just finite dimensional representations of this complex group, but the pi j is an automorphic representation such that Li of SV is equal to L of S of pi 1 R1 up to L of S pi M Rm. So if functoriality is true, each representation of this is like that is equivalent to one like this, but where here pi m is a representation of a GLN. But even if we can't prove functoriality, this is not such an uninteresting statement after all. So let's try to dissociate this problem from functoriality and see if when we can prove that. Well, what kind of varieties can we deal? You recall that basically in the 50s this was done for 1 billion varieties of CM type. The last statements of the last sort were proved. And then in the 50s and 60s, people dealt with modular curves. So if I take the upper half plane H, so the upper half plane, take a gamma, which is actually a congruent subgroup, then I divide the upper half plane by gamma. This is an algebraic curve, not complete, but I can add a few points. And if I add those few points, I can define it over, actually define at least over a number field, defined over a number field. With a clever choice of gamma, that number field can be Q. And that's a case that can be dealt with, and is known as the Eichler-Shimura theory. The Eichler-Shimura theorem says that for this quotient, which is basically an algebraic curve that can be defined over a number field, in particular over Q, it's really over Q, then this statement is true. I pointed out at one of the early lectures that the fact that the statement is true over Q does not mean it's true over other number fields. It's not necessarily. Now, the next class of varieties that one has begun to handle, this is a special case, but a more general class of varieties, are the so-called Shimura varieties. Not so-called. Actually, I think I'm responsible for the name, so I shouldn't use so-called. And these are efforts, of the 70s, but the 80s, and very slow effort in that time. But I think now these efforts are finally coming to fruition, especially in the work of Kotlitz and something can be done. Let me give an example. Suppose I take the following bounded symmetric domain. So I take the set of complex numbers z1 up to zn, the sum of whose absolute value squared is less than 1. This is, of course, the bounded symmetric domain, which for n equal 1 is equivalent to this H. And if I take a unitary matrix A in the unit in UN1, then A applied to a point in that space, which has become a column vector, I can write as C Z1 prime, Zn prime and 1, where because A belongs to unitary matrix, the sum of the Zi prime in absolute value squared is still less than 1. So A maps the space into itself. And so if I have a subgroup gamma in UN1, a discrete subgroup, I can divide gamma into H. This time I will get presumably an algebraic variety, but an algebraic variety of dimension no longer 1 but n. So let's take the case n equal 2. N equal 2, this is an algebraic surface. So it's that case that's treated in this book. And the advantage of that case is the following. Let me explain briefly. Kottwitz can handle more general cases, but this is the first case in which all possible difficulties appear. All the difficulties that you will meet in a general case you meet here. Now, of course, you meet them here in mitigated form. The fundamental lemma, as I mentioned, is much easier to prove in this case, hasn't been dealt with in general. Problems arising from the compactification, from the fact that these varieties are in general not compact, they have to be compactified. The compactification introduces singularities that then have to be resolved and so on. These things are much easier to deal with for the case n equal 2 than they are in general. But those two cases, so endoscopy, those two problems, endoscopy and non-compactness, are met here, and also certain counting problems. The counting problems can be solved in general, but not in general, but the counting problems can be solved in the problem of actually describing the number of points on the reduced varieties can be dealt with quite generally for Shimura varieties. These two problems, this problem is giving way, but this one is really hard. But all these difficulties are seen in the case of these Picard modular surfaces. So in that case, they're more interesting than modular curves, and they're more interesting than the one other case of Shimura varieties that has been handled completely, namely the Hilbert-Blumenthal varieties associated to GL2 over a totally real field. All right, so let's just see what we're going to do for these. So I'm going to describe to you now results that are in this, that are proved pretty much in that book. So what's this group gamma? So by the way, when you really do Shimura varieties, you think of them as being associated not to gamma, but to a GQ contained in GA, and G is a group over Q. And in that case, it's going to be defined by a Hermitian form in 3 variables over E, which is a quadratic extension of Q. So E over Q is 2, so it's just a complex, it's an imaginary quadratic extension. So that would be the group G, and of course it's indefinite. So, but basically the pieces of the variety look like this. This, in this case, as I say, is a 2-dimensional complex ball, and I divide it by a discrete group. That doesn't matter so much for our purposes. The second point, as you'll see, is that the kind of theorem that one is trying to prove, and I suspect that one can, certainly one can expect progress for arbitrary Shimura varieties, And the statement that you obtain will be of this type. Now, that means that it might be an L function that you can handle. For example, for those of you who aren't aware of this, I mentioned it, that if G, for example, if the Shimura variety was associated to the symplectic group, then GL is basically an orthogonal group in 2n plus 1 variables, and the relevant representations here, the relevant groups are usually G itself. I mean, they're not always G itself, but the relevant groups here are often G. The relevant representation then would be a representation of the L group, in this case, representation of SO2n plus 1, or a covering. It's actually a representation of the covering, and in fact it's the spin representation. And these L functions cannot be dealt with for the spin representation, except in the trivial case when n equals 2, and trivial when the spin representation, I mean, when the orthogonal group and the symplectic group are the same. So, however, in the particular, as we'll see, in this particular case of the Picard surfaces, the L functions we get are really L functions associated with GLN, and so they can be managed. So not only do we, in this case, do we obtain a statement of this sort with identifiable L functions on the right-hand side, but they're L functions that we can whose analytic properties we can handle. That means that the analytic continuation of the Hasse-Weil zeta function poses no problems for this surface. All right? You look puzzled.
Yeah. What is the analog back in SL2R of this? That's just like saying that the.
It says that if I take a modular curve C, L1, so the interesting part of this is equal to a product of L of S. You see, the group here is GL2, and the R is the standard reference.
Corresponding to a special congruence subgroup or something.
Yes.
Yeah.
Okay. Okay, implicit here, and I don't ever mention it explicitly, but I have to here introduce some sort of congruence condition. All right. So what we understand is that if we have a Shimura variety associated to a group G, G is not the only group here, but it's the one of the groups here, and it's the major one. And that means we have to have an R. Now we can define the R in general, but let's see what it is in our particular case. So in our particular case, the main group is now, it's not true that the main group is U3. The main group is the general unitary group, those linear transformations that preserve the Hermitian form up to a scalar. Now that scalar is, as you can imagine, a nuisance. Let's forget it. You have to put it in, otherwise the variety is not defined, but it means that every time you have to write things a little bit differently. So let's pretend that G is this group. It's not quite true. Then GL is, as I've said many times, GL3C, semi-direct product with the Galois group of K over Q. Now the basic field is Q. And K, I might as well take here, it will be suffice for our purposes to take K to be E. That's the quadratic extension we take. What's the relevant representation? Well, we start from R0, which just takes GL3C to GL3C. It's just the ordinary representation of GL3 as itself. And then the R, the pertinent representation of the L group, would be the induced to GL from this group, which is the L group over E of R0. So this is R. Now, so the interesting L function would be L of S pi R, where pi is some automorphic representation of the group. We expect to be able to express the Hasse-Weil zeta function of our variety in terms of these things. Now, R is sub R, but this is just equal to, base change is such that this is equal to L of S pi E R0. This would be the L function of a variety thought of as some kind of variety over Q. But the real field of that definition is E, and this is the more natural thing to take. So by and large, we won't have this, we'll have this. And as I said, this is just the L, this is just L of S pi E. This is just the L function studied by Jacquet and Gaudemont associated to pi E. So this is something that can be handled by Fourier analysis. Now, but we know the dangers of endoscopy. We know that R restricted to H, say, HL. Remember, HL was a group whose connected component was basically the 2 by 2 matrices sitting in G hat, which was GL3C. And we know that the representation H was basically U2 cross U1. And we know that the representation theory of H plays an important role in studying the representations of G, that particular functoriality, and in particular R restricted to HL is reducible. That's more or less clear. It corresponds to the fact that R0 restricted to H hat is reducible. That means that if pi belongs to pi sub c, this was the Arthur parameter, and c factors through HL, then L, you see L of S pi R. So pi, that means that pi really would, in a certain sense, pi is in some sense an image of functoriality of pi prime to associate to HL. And this is equal to, everything works such that this is equal to L of S prime, pi prime, and R prime, where R prime is equal to R restricted to HL. But this, if you think about it, is the sum of a one-dimensional thing, R1 prime. So this is equal to R1 prime plus R2 prime. Think about it as the sum of a one-dimensional representation corresponding to this piece and a two-dimensional piece. I mean, if I go back to the level of R0 it is anyhow. So the L function factors, and what that means is, I really have to go back, and I'll do it later, to look at this thing. This thing, which is something of degree 3 associated to something of degree to a three-dimensional representation of GL3, really factors naturally into two L functions, one of degree 2, one of degree 1. And I'm going to have to face the question, do I want one, the other, or both? All right? They may not all be relevant. That means that in addition here I basically had the group G itself, or if I preferred I could go to the group over E, which was just GL3. Then I'm going to have to put in GL2 and GL1 over the quadratic extension as well. But it's not clear how. All right. All right, so let's just, now we have to ask ourselves a question. We're trying to examine these L of Si V. This is the Shimura variety, and we're going to have a contribution to these things from automorphic representations of GAF. How does this work? How does this work? Well, let's see. We can write this pi as a tensor product of some representation of G of R with some representation of G of AF, of the finite adels. Now, I want to think of pi contributes to the cohomology. In other words, we know, so far as we're familiar with, so to speak, the standard facts from algebraic geometry and number theory, that this Li of SV has something to do with the ith cohomology of V. So the first question would be, say, to look at the situation over the complexes and say, how does pi contribute to the cohomology? Well, those of you who are familiar with say, what appears in the book of Burrell and Wallach, various other places, will know that there is a way to compute this which is known as Matsushima's formula. In other words, the contribution of pi, just in the complex sense, to the cohomology is related somehow to the cohomology of this representation pi infinity in the so-called GK cohomology. Doesn't matter what this is, something defined over the complexes. I think that you wrote a book about them. So it's related to this. So the only pi's that are relevant are those of cohomological type, so for which that's non-zero. So the pi infinity of cohomological type. Those are the only ones we want here. So if we're worrying, say, about the contribution of pi f, we think not the contribution of pi, but of pi f, the question is whether we can put pi of f together with pi infinity of cohomological type to make an automorphic representation. So we start off, we may have a pi infinity tensor pi f, pi infinity prime tensor pi f, and it'll always be only a certain finite set. I mean, there are only certain finitely many pi infinities that, in fact, are of cohomological type. But we fix pi f. We fix pi f, and we look at them all and see which are automorphic. Some will be automorphic, some won't. But they all lie in a particular Arthur packet, pi of c. This Arthur packet will be determined solely by pi f. So there is a C floating around. And it will play an important role. Now, one other thing that, we didn't do this, but V is defined by an open compact subgroup K in GAF. And we haven't defined a Shimura variety, so we haven't talked about this, but we need that pi of f contains the trivial representation of K, sort of a positive number, M pi fk times, positive number of times. So it's understood that the pi f contains the trivial representation of K, and whatever contribution pi f makes, it makes it with that multiplicity. All right? So there'll be some contribution from pi f, and it will appear on the right-hand side repeated that often. And now I will now forget that m pi of k. It appears as an exponent. In other words, you just think of it as appearing as an exponent here in the contribution of pi f. So we're going to examine the contribution of pi f without this exponent. We have to put the exponent in, but it's uninteresting, provided it's positive. And the question of whether or not it's positive, of course, just depends upon whether we've chosen to define the Shimura variety by means of a sufficiently small k. Okay. Well, let's look at an example. Remember, everything now, we have C around. They all belong to pi c. It's a good deal determined by C. Let's look at the case that C restricted to SU2 is irreducible. Now, we know what that means. We know then that pi f is one-dimensional. On what we know, we have a surface. We have a surface, so there's cohomology possibly in dimension 0, in dimension 1, dimension 2, dimension 3, and dimension 4. The one-dimensional representation contributes, so for I equals 0, 2, 4. So it contributes in dimension degrees 0, 2, and 4. It actually, for each of them, it contributes what? I mean, pi of f, we know, pi, as we saw last time, is associated to a character chi of GL1 AE, and the contribution is LS minus I over 2 chi. I've cheated because, as I said, I was pretending that U3 was GU3, so the formulas are simpler. So each pi f contributes, and here is, so this is Li of SV, the part of the zeta function coming from cohomology in degree I, contains this as a factor. Well, the multiplicity here is 1. Let me just observe that I can do the following. Suppose I take Re and compose it with psi restricted to SU2. Right? The psi is the irreducible three-dimensional representation, I mean that's what I've assumed, of SU2. And I compose it with R as just the embedding. So this is just the psi itself. Suppose I apply it to the matrix X inverse, or if you like, X 1/2, X minus 1/2. Then I get I get X, let me do it this way, X1, X squared 1, X to the minus 2. So you see, what I wanted to say is that I can read off from this psi on SU2 how the Hodge types are going to be distributed. I mean, you think, I mean, these three pieces, right, are all going to be obtained from the first by multiplying by the fundamental class. And I can read where they lie just by looking at what psi does on SU2 and composing it with Re. This is a general phenomenon. So we'll see how that works in other cases. So this is, in that sense, this C of Arthur's conjecture tells you something about the Hodge types. I mean, they tell you how to speak, how you get, I mean, it doesn't tell you everything, but once you know, so to speak, the primitive cohomology classes, C tells you how to do the rest. And it tells you where what degree the primitive cohomology associated to pi is going to sit. All right, now what else do we know? All right, another possibility, well, let's go over here. We know what can happen with this C. We could have C restricted to SU2, to the SU2 was a direct sum of a one-dimensional piece and a two-dimensional piece. both irreducible. So one-dimensional piece is obviously reducible. So in that case, pi of psi infinity contains two representations. This was a case we studied last time, but we fixed pi f. Pi f is fixed. And for only one of these two, only one, say pi infinity, is pi infinity tensor pi f automorphic. As I said, embedded in Arthur's conjecture is a description of, is a prescription rather that tells you how, given pi f, you determine which of the two pi infinities is pertinent, occurs here. They don't both occur. Now, what we saw also that in this case we saw that the elements of pi sub psi, pi of psi, are defined by two characters of GL1AE. I think I just adumbrated that the last time. I alluded to it without going into too much detail. I don't want to go into any detail here because it becomes messy, but this is true. In other words, what I said, well, psi restricted to SU2 is one-dimensional piece and two-dimensional piece, therefore psi restricted to the LF part is a direct sum of a two-dimensional scalar and a one-dimensional scalar. It gave me these two characters. Well, you see there are two possibilities here. As I said, I don't know what pi infinity is without going into the details of Arthur's conjecture, but depending upon which it is, there are contributions to cohomology in dimensions 1 and 3. So I have none here, something in dimension 1. Or there's contribution to cohomology in dimension 2. And in both cases, the contribution to the L function, L sub I of S and V, for I equal 1 or 3 in this case, or 2 in this case, is L of S minus I over 2. And then there is some character, key is a character of GL1AE, which is somehow built up by taking product or quotient or something of the two characters defining C. So in this case, the relevant L function is associated to a GL1. If, by the way, I take RE composed with C in this case, well, it's the direct sum of a one-dimensional piece and a two-dimensional piece. And so the one-dimensional piece just is trivial if I take the image of this X and X inverse. And if it's a two-dimensional piece, it's X and X inverse. So in ways that depend upon the details of Arthur's conjecture, this case is somehow related to this, where there's only primitive cohomology in the central dimension. This case tells me that the relevant cohomology is one. Those are stars, not x's. Is out 1 degree on each side of the middle. So I can read it off if I know the details of Arthur's conjecture. I can read off, so to speak, where the contribution to the cohomology is going to come just by knowing what C looks like on the SU2. Now, what we're not finished yet, but we're going to discover that there are no other representations. See, we said if C restricted to SU2 is the sum of a one-dimensional piece and a two-dimensional piece, then the pertinent representations for one of the two possibilities for pi infinity contribute to cohomology in dimension 1 and 3. We'll see that otherwise they don't. We saw they didn't. We didn't before. Here this was the trivial case of 0, 2, and 4. We'll see there's no other contribution to cohomology in dimension 2, in dimension 1 and 3 rather. So what do you see? In dimension 1 and 3, all the L functions are abelian. They're associated to one-dimensional representations of GL1AE. All right? Now, that says something about the arithmetic. Dimension 1 is, of course, the Albanese variety. And it says what we've just discovered is that the L function of this Albanese variety, at least the part in degree 1, is entirely abelian. So the only possible conclusion is that this Albanese variety is of CM type. As I said, that expectation is confirmed in the paper of Kumar-Murthy and Ramakrishnan in this volume. So our knowledge of the zeta function leads us to the fact that the product of abelian L functions leads us to this conclusion, and this conclusion is correct. All right. The final case. Now the final case is C restricted to SU2 trivial. Now that means that C is born by LF or even by LE. It's the restriction of C to LE that matters. And we have seen before, we saw last time, that there are two possibilities formally that C restricted to LE is irreducible, or, by the way, the connection between the restriction of C to SU2 and the Hodge types tells us now that all the contribution to the cohomology, the contribution to the zeta function is all going to be I equal 2, all going to be in the middle dimension, because the representation of SU2 is trivial. So the two cases, psi restricted to LE is irreducible. Then psi corresponds, we know, to an automorphic representation, pi e. So how do I put it? In that case, we saw that in that case, and I said it, that we were free to modify pi infinity in pi of C infinity any way we liked. If we had one pi infinity and pi C infinity that was an automorphic, then they're all automorphic. So there's no constraint in this case. There's no endoscopy in this case. They're all there. And what we see, so what we have is that the contribution is all in degree 2. It's L of S minus 2 over 2, S minus 1. And you can think of it as being either L of SE of the base change of any of these things. They all base change. You can either think of L of S minus 2 over 2 CE. This is an undefined object. It's the representation of LE that doesn't exist. But this is, according to our convention, just this object, which is well understood and analytically continuable. So that's the contribution in this case. It's an L function of degree 3e. This is wrong. I should put R0 composed with CE. Three-dimensional representation of LE. That was one possibility, that this is irreducible. The other possibility is, as you know, basically that C factors through HL, so C factors through HL. So this says that C is reducible. Well, actually, I think in this case, C could be, so CE reducible, so CE could be formally one-dimensional plus two-dimensional. Actually, in some sense, it could also be one-dimensional plus one-dimensional plus one-dimensional, but that's not pertinent, as I recall, for cohomology. It's this. So, Li of S is B. The contribution, so that says that, see, I can think of the following. CE takes LE, if you like, to H to G hat, which is GL3, but it really factors through H hat, so it's really two pieces. This is one-dimensional plus two-dimensional. So R0 composed with CE is really the direct sum of a one-dimensional representation of LE and a two-dimensional representation of LE. And what I have to put in here is L of S minus 2 over 2. It's only for I equals 2 that this counts. And then I have to put in Ri, where Ri could be one-dimensional or two-dimensional. And to know which to choose, I have to go back into the depths of Arthur's conjecture, and that I don't intend to do. But in any case, this is Ri composed, this is Ri. This is a representation of L sub E. So this is equal to L of I S minus 2 over 2. And here, it's some automorphic representation, say, let's say eta sub E, either of GL2 or GL1. In any case, it's something that one can handle. So that's the entire picture. We've concluded that, I mean, I haven't said it, but we've put together the contributions of all the pi's of all possible types, and that's the whole zeta, that's the whole zeta function. Those are all, we get each of the L functions entirely, and therefore the whole zeta function. The factors that occur are L functions associated with automorphic forms, L functions of the standard type on GL3, GL2, or GL1 of AE, and so they can be analytically continued, and that's the Hasse-Weil conjecture in this case. So, that's more or less the content of those notes. And I don't know if I should say anything about the proof at all. I don't, whether it's worthwhile. The proof, I'll just say a few words. I'll take in 5 minutes. So, how do we in other words, a good deal of the proof is, of course, to write things in this form, we've had to use Arthur's conjecture in the form that has been verified by Rogowski. But what's the basic identity? It just looks as though we've just used the representation theory. Where does, so to speak, some number theory or algebraic geometry come in? So let me say just a couple of words about that to show you just what the number theoretic ingredient is. So we handled the zeta function, which, as I recall, was product over I even LISV divided by the product over I odd Li of SV. Now, this is supposed to be equal to some product of automorphic L functions, pi I and Ri. This is the general argument. I mean, we're supposed to maybe have some in the quotient in the numerator and some in the denominator. I equal 1 up to m, j equals m plus 1 up to n. So we want to establish a relation like that. In other words, our discussion here said each of these was equal to something, but you can imagine that as a first step we could say that this quotient is equal to a quotient like this, and then we could worry about sorting out the details as to which element here corresponds to which element there later. Well, both sides are products over P, if you like. primes of Q over primes P of Q, or if we look at it more carefully, over primes P of E. So it's clearly a statement like this is really a statement about the individual factors, one for each prime. So we look at a given prime, and we might as well look at logarithms. So we look then at minus the logarithm of the left-hand side at a given place P. Its summation from n equal 1 to infinity, 1 over n sub n, q to the minus ns. Q is the number of elements in the residue field at P. N sub n is the number of points on the variety at the place on the reduced variety at P. So this n sub n is a number theoretic object. It's the number of points on a variety whose equation is reduced modulo P. I've scammed to some extent the difficulties arising from the fact that I'm dealing with a variety that's not complete, but these are not to the point here. They have to be dealt with, but now, what about minus the logarithm of the right-hand side? This is minus the logarithm of the left-hand side. This will be some complicated thing, summation. Well, you let me get away with it. I don't know what that means. Okay, it's the number of points on the variety divided by n. Means I think that it's late. If I write it, it's some this. You see, it's plus or minus the trace of Rj of A of pi j p to the power n q to the minus nj. You see, we haven't really been working formally with these things, but recall these L functions involve looking at the local components of pi, associating to those local components of pi a conjugacy class in GL, and these are different, GIL in this case, and then applying Ri to that conjugacy class. And this is the kind of thing we have to do. Rj was the representation at the jth place. Plus or minus comes from numerator and denominator. A of pi j p of p is the pth local component of pi. A is the conjugacy class associated to it. We have to raise it to the power n because n is what occurs here, and we multiply by q to the minus nj. So in other words, if we want to show that the left-hand side is equal to the right-hand side, we have to show that this n sub n is equal to whatever we get here. I mean, whatever we get as a is equal to this. We have to show that that's equal to nn. That's the questionable thing. Now, then, what do we have to do? I said this had something to do with the Hecke algebra. This conjugacy class was related to the Hecke algebra. I knew the structure of the Hecke algebra, and so using its structure, I could define these conjugacy classes. That means that these things have something to do with functions on the group. G of QP, in fact. Well, that means that we have something to do with harmonic analysis. And this is the sum, basically, over all pi that occur in L2 of G, more or less. Some are suppressed in taking in the sum. So that this is some expression that I can understand using harmonic analysis. Harmonic analysis, by the way, on which space enriched space on the space G of AQ over G of Q. So harmonic analysis on that space is really the Selberg trace formula. Now, I didn't say it last time, but I should say it. I said that the problem in really doing functoriality beyond the results envisaged by Jacquet and Arthur may or may not involve, but it possibly involves using inequalities in the Selberg trace formula. For those who don't know the subject, I point out that the Selberg trace formula is just Frobenius reciprocity. And so this question as to whether it's possible to use inequalities is an elementary algebraic question. And it's not an analytic question, so it doesn't involve, one can answer the question without being able to, one can answer the question as to whether it might be possible to use inequalities without being technically in a position to do much about it. But you can, there are people who are technically in a position to do something about it if you have an idea. In any case, here we do the same thing. This has something to do with harmonic analysis. We apply the Selberg trace formula, which is Frobenius reciprocity. And we play with it, and this becomes then a sum of orbital integrals of elements on conjugacy, on rational conjugacy classes. Let me put it that way. We certainly don't want to go into detail at this point. If we're not in a condition to recognize that n sub n should have appeared in the numerator, not the denominator, we don't want to go into these details. Now, the only point is to say that that's the right-hand side, so all we need is something similar on the left-hand side. If we have something similar, we can do it. So all we need to do is to express the counting function n sub n in terms of conjugacy classes. In GQ. This turns out to be a difficult problem really in about a billion varieties over finite fields. But a very concrete problem about a billion. But the relation between a billion varieties over finite fields and semi-simple groups, and it was solved in various forms by Riemann, Zink, by Kottwitz, and then later apparently by Ventin-Berger in the context of Fontaine's theory. It was somehow clear, I think, it was always clear, and this was clear, that, it has something to do. When you use that, one has to use a billion varieties over finite fields, and say the theory of Fontaine was built for that, so it's no surprise. But in any case, these people solved the relevant problem in the form necessary for application in particular to this case, but also to other Chamour varieties. And that's just a sketch of where the proof comes from. The pertinent point is perhaps, that's not the only pertinent point, but one pertinent point is that now these Picard modular surfaces should be accessible. One should be able to treat Picard modular surfaces the way one treats modular curves, so that it makes sense to ask concrete number theoretical questions about them because the tools are there for responding. Okay, thank you for your attention.
May I ask, it was very clear that you had a finite choice of finite. And that's carrying along a tremendous amount of information. I mean, you just, what are you doing? Just choosing something in each place, or do you know?
What do you mean? I mean, basically, I could have done it another way. I could have said, I could have organized this thought a little bit differently. I could have said, run through all possible C, such that C infinity belongs to a certain finite set. All right, such as the corresponding pi's and pi infinities of cohomological type. Of what? Of these C's? Yes. But on the other hand, for only finitely many is this number m of pi f k positive for given k. Right? I mean, there are infinitely many, but m pi f k tends to be 0 unless k is sufficiently large. Right? And if I fix k ahead of time, then I exclude all but finitely many pi f.
Now, once you've tied, you basically have this equality of all these.
So each possible pi f contributes to the Zeta function. So I mean, for the Aiko-Shimura theory, it's the same thing. Right? Each time I have the same thing, each time I have I mean, in that case, I usually exclude the case where there's only contribution degree 0 and 2. Here it's more complicated, so I include it. So I'm only left with things that contribute in the middle dimension.
Yes.
So that means that this sign infinity is fixed. So one sign infinity that's interesting in that case. And then I take all possible pi f's that will match up to the sign infinity.
Yes.
Whenever I have one.
And you have a way of deciding that in some reasonable way.
No.
Oh.
I mean, I can't tell you what. I can't tell you whether the only way I know to decide whether representation is automorphic is to say automorphic. And
well, isn't the information hidden in knowing which pi f's work? Isn't that telling you whether you get this match of the geometric numbers and the algebraic numbers?
I was formulated as following. If I have an automorphic representation, then there is a contribution to the Zeta function. And that is the only type of contribution to the Zeta function. So I've succeeded in describing the Zeta function in terms of automorphic representation. I think neither I nor anyone else can do more.
Well, I mean, in the classical theory, if you have a cusp form, you can start computing coefficients. And if you have an elliptic curve, you can start computing numbers of points.
I mean, that information is pi f.
That's all that information is concealed in pi f.
Yes.
Right?
Yes.
I mean, what cusp one form is.
If I have pi f, I can compute, for example, if I want to, once I have my statement, if you say, but what's the value of LIS, say in P, at 1/2, 3 halves, whatever the pertinent number is, I can compute it. I can compute it because that much information I can get. I can look at the space GA over GQ. I can study it. I can find the eigenfunctions of the Heck operator numerically. Once I find the eigenfunctions of the Heck operator numerically, I can compute them more or less approximately. I can analytically continue the Zeta function as far to the left as you want. In particular, I can compute that number with any degree of precision that you would like. So that's what I mean. To say I have another, to say that I have, to say that I mean, when I have an L function of this form, this is the representation of G of n, then I can tell you anything about it except whether all at 0 is long enough to put. So I can particularly I can compute it to any degree of precision. Yes. And I can combine them all. It's a soluble finite problem. Just as it is for GL2. They may not be quite so nice because dealing with don't have simple holomorphic thing.
What's the question?
Could you expand on a bit more of one one?
Yeah, exactly what?
What the connection between Boolean varieties and
All right.
left it somehow.
Let me do it, say for this effective group. All right. let me do it. So I can do it for this case, but let me do the symplectic. So the group G is the group of symplectic similarity. All right? What is the corresponding? And let me choose K to be the set of all GAF that K G integral. So this is ZF such that G is congruent to 1, say, modulo some number n. Then what is the corresponding Chamour variety? So this is the Chamour variety. The Chamour variety is a solution of a moduli problem. The moduli problem is, what I need is, so V, so every point on V is another kind of object. What I mean, V parametrizes some kind of object, namely V parametrizes an abelian variety A of dimension, so this is the general symplectic group in 2n variables. So A parameterizes an abelian variety provided with a polarization, presumably principal, and with an isomorphism of the points of order n on A with the standard group. So every point on V is another kind of object that it has this, this, and this. That's on V over C, but that's also on V over FP. Right? So in order, what I mean here is that these gentlemen know how to compute, how to parameterize these objects in terms of group theoretical data. All right. Do you want me to say more? If you see, I don't know if I can in any intelligent way. Let's see if I. Can I do it? Can I? The problem is, without saying much more, the problem is roughly the following. If I have one of these objects over Fp, I can lift it to something over, say, Zp and therefore over Qp. All right? I can lift it to something of Cm type. So lift it to something with lots of endomorphisms. All right? That means basically if I start with an object, see, so I can lift it to an abelian variety like a Cm type over Qp or over Q bar even. Now, such an object really corresponds, if we think about it for a bit, it corresponds to a Cartan subgroup of G over Q. I can attach to it a Cartan subgroup of G over Q. All right? Now, the difficulty is that I can recognize that Cartan I can almost recognize that Cartan subgroup. I can recognize its conjugacy class over Q bar. All right? I can recognize, I mean, just so to speak, from this original thing. I can recognize it over Q bar. I can recognize that Cartan subgroup over Q bar. I cannot, however, easily recognize its conjugacy class over Q. And that's the problem that they solved. And that somehow was not a problem that was posed within the classical theory of complex multiplication of abelian varieties over finite fields. The problem of getting a hold of that Cartan subgroup in Q. And that's what they did. Okay. Now I will stop. Thank you.